Hi everyone, thanks for coming to my talk today. I'm Shashank Srivastava from Carnegie Mellon. And today I'll be talking about some of our work on learning to classify from natural language explanations. So if you think of the last 2 decades of NLP research, almost all of it has been about how statistical learning can help improve the state of natural language understanding. The body of research I'm going to present today now is part of a smaller body of research which actually explores the opposite question, which is, can natural language interactions actually help machines learn better? So before I begin, I'd like to mention that this is joint work with my collaborators, Igor Labutov and Tom Mitchell at CMU. So imagine that you want your personal mobile assistant to manage your important emails. So for example, you might want it to send you a reminder if you haven't read an important email for several hours. So in order to be able to do this, the agent would first need to understand what this notion of an important email is. And how would it know this? So ideally, you should be able to explain to the agent what an important email might look like, so that it can then use this information to decide if a new email is important or not. So for example, you might say things like, emails from my mother are usually important. Such emails mention a deadline or a meeting. The subject might say urgent, and so on. And in essence, this is the problem that I'll be talking about today. How can you learn classifiers for concepts such as important emails from natural language explanations, which look like these? However, before I begin the technical part of my talk, I'd first like to briefly mention the motivation which fuels this research, which is our hope that NLP can actually make machines learn in more human-like and more effective ways. So usually when we think about machine learning, at the back of our minds we are thinking about large passively acquired collections of data. And this is with good reason. The inductive learning paradigm has been widely successful across a range of application tasks. But the problem is that this dependence is actually infeasible for the long tail of real-world learning problems. And this is because real-world learning tasks are often domain-specific or even individualized. For example, my notion of what constitutes an important email might be different from yours. Second, there are inherent statistical limitations on what can be learned from labels alone. So learning theory tells us that the number of examples we need roughly scales as the log of the size of the hypothesis space. And what this means is that it should be intractable to learn common knowledge representations like ontologies, which is obviously bizarre, because this is something that children seem to learn with relatively few examples. So the reason for this dissonance might be that traditionally, machine learning has largely ignored richer forms of input. So if you consider the ways in which people learn, they do learn from label, examples and observations, but they also learn from a blend of other strategies, including things like explanations, instructions, asking for clarifications, and so on. In particular, if you think about human learning and pedagogy, the processes involved there seem to be those which are all intimately connected with language. So think about reading books, listening to lectures, engaging in student-teacher dialogue, and so on. But there's a bigger reason why we should all care about learning from language, and which is this. If people could teach computers using the language of humans, they could be way more useful than they already are. So today, if I want a new capability on my phone, I need to wait for some engineers at Apple or Google to implement that software. But just imagine if people could teach computers using the language of humans, the sorts of things that might be possible. So you might say things like, if there's a new publication relevant to my project, email it to me. if the weather is going to be bad, let me know. And if I receive a late night email from my advisor, ring the alarm at full blast. So potentially what this could allow you to do is, rather than have to rely on software programmers, this could potentially make every phone user a programmer. So there are two core issues in any formulation of learning from language. So the first is the basic question of learning to interpret language. And this basically refers to the challenge of how do you get from free-form natural language text, which looks like this, to some kind of symbolic representations which in some sense represent their meaning, but more importantly, which are things that computers can process and reason over. And this conversion is usually referred to as semantic parsing. So the first question we need to address is, how can you effectively learn semantic parsers? And the second question is, even if you could completely, perfectly interpret language, how can you use those interpretations to actually operationalize learning? In the sense that even if you could completely parse language to these logical forms, how do you use these interpretations or logical forms to get to a concept model or a classifier which can tell you whether a new email will be important or not? So I'll partially talk about both these questions in my work today, but this talk is going to be mostly about two distinct ways through which natural language can operationalize learning. And these two aspects constitute the two parts of my talk. So first I'll be talking about some work on how natural language can be used to define rich and expressive features for concept learning tasks. And secondly, I'm going to talk about how language can be used to specify model constraints that can directly provide supervision for training classification models. So the first part appeared as a paper at EMNLP last year, and the second part appeared at ACL earlier this year. So let's begin with the first part of my talk, which is about using natural language explanations to define feature functions for classification tasks. So any successful applications of supervised learning generally rely on a process of feature engineering even before any learning actually takes place. So this involves the design of features which define the variables in which the learning problem is defined. So for example, we can think of natural language explanations such as emails from my boss are usually important as a feature for any email, which only fires if an email actually comes from my boss.